So what we're going to do now is we're going to go over how to take our table data, which is our two variable data, plug it into Desmos, and then use Desmos to create a function that models the relationship that we see going on. First thing we got to do is we've got to insert our data. So we should see just a bunch of points after we put it in. If you click this plus sign up here and then click on table, you'll see it says X1 and Y1. I'm just going to put in some random points. So we'll go with 20. So I got a couple here. We'll go with 17, 15, and 13. Now, if you don't see anything on your screen, sometimes you just have to zoom out a little bit so that you can see them. And if I look at these here, don't have a ton of points. If I let's put a couple more points in here, and we'll go here, and we'll put one last one here. So if we look at this, first thing we have to do is we have to understand what general relationship do we have here. If I'm looking at this, I know it's not a perfectly straight line, but this looks like it's going to end up being a linear relationship to me. So I think that I can model this relationship with a linear function. Because if I draw a straight line, I think the majority of these points are going to be on it. Now, what I can do to model that is over here now, where it's asking for my function. I know that y equals mx plus b is my linear function. So what I'm going to use is I'm going to use all of these points. So instead of using y, I'm going to call it y1. Because if I look up here, that's what these are called. All these values are called y1. So I'm going to say y1 is approximately equal to, notice I have that approximately equal to sign, not an equal sign, but an approximately equal sign. And then I'm going to type in my m, and I'm going to say x1, and I can see this pops up here. So I've got my x1 here, right? And then the last thing I want to do is put in my plus b value. So you can see I'm putting this information in, and it creates this blue line for me. This blue line, we can see it doesn't go through all of the points exactly, but it pretty much goes through the majority of them. So that's going to be the function that best models our situation. Now down here in this area, it tells me the parameters. Those are the things that I'm interested in. So if I look at it, I have to find a slope and a y-intercept if I want to find what the y equals mx plus b form is. And it tells me right here. So it takes all of our information, right? We tell it, well, it's a linear equation, so we give it the approximate linear equation using y1 and x1, and then it tells us what the m value should be and the b value should be. And if I want to check that, I can plug that in. If I put y equals m, which is negative 2.32143 times x, plus whatever my b value is, which in this case is 19.6786, I can see that red line. If I do this, I'm just toggling it on and off. It is right over top of that blue line. So this information here is telling me what my information is, my slope and my y-intercept. Okay, so we don't have to go through doing all the calculations ourselves. Desmos will do that. And what we have to do is we put in our table, and then once we have our table, we put in the approximate relationship. We know it's linear. The only difference is instead of just calling this y and x, we have to call it y1 and x1, because that's what we called it up here in our table. And I have to put in approximation sign instead of an equal sign, which should be up in the top left corner of your keyboard. So that's for a linear function. Now, we can do the same thing for an exponential function as well. Here I put values in for us. I've got 0, 20, 1, 12. You can see all of these points here are plotted on this graph here. Now if we look at this one, we can see that situation where it's decreasing very quickly and then it's kind of coming to that steady halt. We can say that's going to be an exponential decay problem. And then remember, our form for an exponential decay would be y equals a times b to the x power, right? Now, if we want to come up with a line that's going to model the one we have here, we have to use y1 and x1. So where I have y, I'm going to type y1. Where I have x, I'm going to put x1. Oops. So x1, and then the last thing I have to do is put in my approximation. So I'm saying that y is approximately equal to a times b to the x to the 1 power. So it's using these points to calculate our a and our b value. And if I look down here, well, first if we look over at the graph, you can see this red line is pretty much going through, if not close to, all of our green points. And I'm just following along here so I can find it at different values. But it also shows me here, oops, I'll zoom out of that. It shows me over here what those parameters would be. So if I want to create a relationship or create a function that models the points that I plugged in, my initial value, which is my A, would be 20.4054. And then my growth factor, or in this case my decay factor, since it's getting smaller each time, would be 0.527187. And if I plug this in, just to make sure it looks good, we'll put 20.4054, and I like to put it in parentheses my B value, which is 0.527187, and I raise that up to the x power. You can see now this blue line is going right over top of that approximated red line we created. So we can see the initial value that it calculated for us was 20.4, and the B value, which is the decay rate, is about right around half. Now if we look at our information, we can see that's pretty accurate. Our y-intercept should be right around 20, because when x is 0, y is 20, which it is. Our our initial value, is 20.45, so it's close on that aspect. Then if you look at these, I mean, it's almost going down by half each time. If I go from 20 to 12, a little bit less than half. 12 to 5, a little bit more than half. 5 to 3, a little bit less than half. 3 down to 1, a little bit more than half. 1 to 0.5 is exactly half. 0.5 to 0.2 is very close to half. 0.2 to 0.1, we're cutting that exactly in half. So you can see that these B values, this 0.5, is approximately what we are multiplying this number by each time to get this one. Or in this case, we're pretty much just approximately cutting our numbers in half. So we can really use Desmos, and this gives us a lot of information in a very simple way. The only thing you have to know is once you get your table plugged in, you have to be able to say that this is a exponential model, and you plug in your exponential approximation, or it's a linear model, and you plug in your linear approximation, and then it'll do all of the work for you, which saves us a lot of time, which now we can interpret this, and we can use this function to solve different problems.